There are many forms of energy. Before we define energy per se, let us derive from what we know how to define a special type of energy called kinetic energy. Let us start with an example of the trajectory of an object, which could be in 3 dimensions, but for ease of representation, here we will still work with a 2-dimensional case. We pick a point on this trajectory and draw a vector velocity at that location. Recall that velocities are tangential to the trajectory. This velocity is in the same direction as a tiny vector displacement delta d occurring during a tiny time interval delta t around that time. Let us add a blue vector representing the net force on the object at that time and split this vector into 2 parts, one parallel to the velocity, called the tangential force, and one perpendicular to the velocity, called the centripetal force Fc, not to be confused with the contact force that used a similar symbol before. The sum of these 2 forces is the net force. These 2 forces have a different effect on the velocity. The tangential force modifies the speed of the object only. The centripetal force modifies the direction of the velocity only. So speeding up or slowing down are due to the tangential force. Let us consider such a tiny displacement along the trajectory that the tangential force is nearly constant over that displacement. Recall some of the kinematic equations valid for constant acceleration for a general set of 3-dimensional reference directions. If you add the 3 equations together, the sum of the squares of the components gives you the square of the magnitudes of the final and initial velocity vectors. This is valid for any choice of constant reference directions, so let us choose one set where the x reference direction is in the same direction as the velocity, i.e., in the same direction as the tiny displacement delta d. For this special choice of reference directions, delta dy and delta dz are 0, and the previous equation simplifies to this equation, where the ax is labeled as a parallel, to remind you that this special choice for the x reference direction is in effect. Notice that delta dx is now equal to the magnitude of the tiny displacement vector. If the tangential force is in the same direction as the velocity, the component of the tangential acceleration, a parallel, is positive. If the tangential force is in the direction opposite to the velocity, the component of the tangential acceleration, a parallel, is negative. So we ended up with this equation on the previous slide. Remember that at this stage, it is only valid for a tiny displacement where the tangential force is approximated to be constant. Let us multiply this equation by the mass of the object on both sides and divide by 2 on both sides. Collecting all the terms with speeds on the left-hand side and using Newton's second law gives this. F net parallel refers to the component of the net force parallel to the velocity, which is the same as the component of the tangential force. Just like the component of the tangential acceleration, F net parallel is positive when the tangential force is in the same direction as the tiny displacement, and it is negative when the tangential force is in the opposite direction to the tiny displacement. The object is speeding up when F net parallel is positive, because when the right-hand side of the equation is positive, the final speed, Vf, must be larger than the initial speed, Vi. The object is slowing down when F net parallel is negative, because when the right-hand side of the equation is negative, the final speed, Vf, must be smaller than the initial speed, Vi. Finally, noticing that the left-hand side of the equation is the change of the quantity mv squared over 2, we can write this expression. The expression inside the bracket on the left-hand side refers to what is called the kinetic energy of the object. We will use the variable named Ek for the kinetic energy. With this definition of the kinetic energy, we can reduce the kinematic equation to this expression. We have just defined a quantity called the kinetic energy as being half of the product of the mass of an object and the square of its speed. So the faster an object moves, the more kinetic energy it has. A small car moving at 100 kilometers per hour has less kinetic energy than a large truck moving at that speed because the kinetic energy is proportional to the mass of the object. Notice that kinetic energy is a scalar. It does not have a direction in space, and it is always positive or zero. Using the usual SI unit for mass and speed, we find that the measurement unit for the kinetic energy is kilogram meter square over second square. This combination of measurement units is typically known as a joule. It was named in honor of James Prescott Joule, a physicist that did a lot of experiments about heat and mechanical energy in the 19th century. Another warning: this definition of kinetic energy is only valid at small speed. Small speed meaning that the speed of the object is several orders of magnitude smaller than the speed of light. The more general definition for the kinetic energy will be left to be introduced in a more advanced physics course. The physical situation we will study will only involve small velocities, for which the definition of Ek introduced here is perfectly adequate. To conclude this lecture on kinetic energy, let us study a numerical problem. For this example, there is no need for a drawing to define reference directions or to show a free body diagram. Let us go directly to the list of givens: the mass of the object and the speed. We also need the equation defining the kinetic energy. When substituting the numerical values for the givens, special attention should be paid to the measurement units to make sure that the final answer is in joules. This means that the mass should be in kilogram and the speed in meters per second. Conversion factors are in order. 1 kilometer was converted to 1,000 meters, and 1 hour was converted to 3,600 seconds. The use of a calculator leads to a numerical value of 1.4 times 10 to the 5th joules. This is our final answer. In the course of this lecture, we encountered an equation involving the change of the kinetic energy. To fully study the potential of this equation, a new physical quantity called work will need to be defined. This will be the subject of the next installment.